All right, so I'm not there. I'm off at badminton. So this unit, I think this lesson can be done um, through just a video like this. So difference of squares is what we're doing today, and the difference of squares factoring, we can best see what's going on by just expanding and simplifying a few uh, pairs that are built in a certain way. So we have x plus 5 and x minus 5. Question is, hey, if the same terms in the front of each bracket, x and x, and the same little terms in the back of each bracket, in this case 5 and 5, but the sign is different. So you have x plus 5 against x minus 5. And the second example is similar, but it's x minus 2y and x plus 2y. If I have a situation like this, then what does it look like when I expand and simplify it? And what we'll notice is that it always looks the same and it is kind of different. And so what we can do then is we can say, hey, here's, if I ever see this expanded result, and then I know I can factor it into these two terms where the front terms are the same, the back terms are the same, and the signs are different. That's what we're going to see. So let's do this then. Let's expand and simplify this first guy and see what happens. So x times x, we're going to get x squared. And then we have x times negative 5. That's negative 5x. Now, it's the 5's turn. 5 times x. It's harder to write on than the screen. And then 5 times negative 5, which is going to be minus 25. All right, so we've done all the products we need to do. And now we can notice that, hey, I have some like terms here. So we're going to group those like terms. And what we end up with is we still have an x squared. And we still have a minus 25. However, minus 5x plus 5x, well, that's 0x. It's just gone. I don't write any x's. If it's 0x, there's no x's. So minus 25 is there. Well, that's a nice little result. Let's see if we get something similar again. So let's try this one now. So let's expand and simplify this guy. X times x, x squared. X times 2y, well, we're going to get, oh my goodness, plus 2xy. And now it's this guy's turn. Negative 2y times x. And then negative 2y times 2y is going to be negative 4x. No, sorry. Negative 4y squared. All right, cool. Well, once again, we see these like terms. And so it's time to group those guys together. So x squared is still just there. Plus 2xy minus 2xy. These are both xy terms. So here I have two of them, minus two of them, 0 remain. I don't have any xy terms. And so I just write down the minus 4y squared, and we're done. Now, this is what it looks like when we expand and simplify. Um, the product of a pair of binomials that share a common first term, share a common second term, however, the sign is different in the middle, right? Let me go back to the pointing. I don't want to accidentally start writing. So, in this case, x in the front of each bracket, right? X in the front of each bracket, 5 in the back of each bracket, with a different sign in the middle. In this case, x in the front of each bracket, 2y in the back of each bracket, different signs in each. What we notice both times is that, hey, in the first one, let me try to move this around so I can. Oh, see, this is what I didn't want to have happen. Moving it around. In the first one, what we're noticing is that, hey, this x squared is really just the first term in each bracket squared. And then we have minus, and that 25 is really just the last term in each bracket squared. Huh, neat. Is that true over here too? X squared is really, yeah, look at that. There's an x in the front of each term, and that's squared. Minus, now 4y squared, is that actually, what is the term in the back here? The term in the back is 2y. So is it true that this is just, look at that. Is that true that it's just 2y squared? Well, 2 squared is 4. Yeah. Y squared is y squared. Yeah, all right, cool. So this works every time, or it worked both times. Now, what does that mean? It means we can go the other way now, right? We can see a pattern here. So let's see if we can apply that same, pattern here. That we can test it by expanding and simplifying back, right? So we have x squared minus 36. Let's factor this using this this pattern. We call this pattern, we call this method of factoring difference of squares factoring. Because if we look over here and over here, these are both differences of two squares. It's two square terms, and their difference, right? The subtracting of the two. So what we're doing is we're saying, hey, let's apply this difference of squares factoring to these little problems posed to us. The question is, let's factor these. So we have x squared minus 36. Well, I know that this is just x squared, and it's minus, and what is 36? Can I write 36 as a perfect square? And yes, I can. It's actually 6 squared. Well, that's awesome, because that means the factored form should be an x in the front of each, a 6 in the back of each, and 1 of each sign. Does that work? And I'm sorry, but due to my space and my, fingers on my little computer screen, I'm not going to physically do it myself, but I'll leave it as an exercise to expand and simplify this x plus 6, x minus 6. Expand and simplify that and show that you end up there again. Right? It works. So let's try example B. So in this case, we have 9x squared minus 25y squared. Wow. Okay. So if this is going to work, if this is a difference of squares, that means that this can be rewritten like that, where um, essentially the square root of the term is in those little tiny brackets, right? I'm saying what was squared to make 9x squared? And what also was squared to get the 25y squared? So looking first at the 9y squared right there, right? I'm going to start using this. Yeah. So looking at the 9x squared, sorry, did I say 9y squared? 9x squared. Well, the square root of 9 is 3, which means, yeah, 3 squared would be 9. Okay. And x squared would be x squared. Okay. Now, 25y squared. And there's going to be a y in the back because y squared is y squared. 25 would need there to be a 5 here. 5 squared is 25. So that means the factored form will have a plus and a minus on each side. In the front of each bracket will go 3x. In the back of each bracket, I'm going to put the 5y. Finished. I mean, you always ask yourself whenever you're doing these, in addition to can I common factor it first? Is it a trinomial? No, it is not a trinomial. Trinomial has 3 terms. So we ask, hey, do I notice that it's a difference of 2 squares? I do. So that's where this is going to come in the big picture of our factoring plan. So now let's go to C. Right? You always ask, and so what I was getting at is, can I continue factoring? Always ask yourself, can I factor further? And 3x plus 5y, 3x minus 5y, these each are done. There's nothing common to anything there, and they're not trinomials. And they themselves are no longer a difference of squares. 100 minus x squared. Okay, well, this looks a little different because now I got x squares in the back. But it never said anything about having to have x's. I just happened to have x's. And in fact, even this one over here, it had y's in the back. And it had stuff in addition to the x's in the front. But that didn't seem to be a problem. I'm just finding square roots of stuff. So I have 100 minus x squared. So, well, 100 is it something squared? It is. It's 10 squared. Minus, that's me getting frustrated. My finger pen ain't writing. Minus, oh my gosh, I'll do it again. Okay, minus, and then, yeah, x squared. So that means I could write it with a 10 in the front of each, an x in the back of each, and a plus and a minus. And there you go. Factored form. Neat. Okay, so it didn't matter the x's in the back. We have a perfect square in the front. That perfect square is 100 because 10 squared is 100. And we have a perfect square in the back, x squared, because x squared is x squared. And it's a difference of squares, so that's good. D. Okay, well, this is getting a little more involved. Look at this. All kinds of stuff happening here. But what's important to note is, as always, we ask ourselves, hey, is there anything common? No, this only gets divisible by 4, and that's divisible by 7. These are x's and y's, this one's a z. So there's nothing common. It's not a trinomial, so I can't do that stuff. But it is a difference of squares because 16 is 4 squared. That's a square. That's a square. 49 is 7 squared, and that's a square. So I'm going to say, well, well, I'm going to have plus and minus, that's for sure. Let's do the back, it's smaller. Doesn't matter what order I do these things, right? 49 is 7 squared. I'm going to need a 7 in each. And I have z squared, so I need a z. Okay, that's a z. So oh, that's a terrible looking z back there. That's not much better. But hey, I'm writing with my fingers on a screen, so I'm sorry it's not as good as it could be. In the front of each bracket, I'm going to have the square root of 16 and an x and a y. All right, there we go. Not bad. There's a little more stuff going on, but it's still um, pretty quick to get that difference of squares factoring done. E. Now, well, difference of squares factoring. 9x squared is 3x quantity squared. 4 is the 2 squared. Oh, see a problem? I see a problem. That's a problem. The problem is there is no such thing as a sum of squares. This is a difference of squares. And we know that because we arrived at this by playing with it, expanding something that was written as the two sets of brackets, and always arrived at a difference of the two squares. Sum of squares is not a thing. So what we're going to just say is that, hey, it's not a difference of squares. So it's not going to be factorable in that way. And you can play around with this kind of thing too if you want to convince yourself. If it's not enough to just uh, see that we arrived at a difference of squares from a certain situation, go ahead and try it. Try to factor it. Say, well, I mean, is Richter right? Does this not work? Can't I tweak it a bit to make it work? Go ahead and try it. I think that'd be great. Play around with it. That's how you learn this stuff, right? So have fun with it. Play around with it. Try to make it work. And in failing that, you'll realize that sum of squares is not a thing. So that's good. So there's no such thing as sum of squares. So that just can't be done. So we don't even, so when you're faced with something like this, you say to yourself, okay, common factor? No. Nothing common among those two terms. Again, there are two terms. Um, Nothing common among the two terms. Um, Trinomial factoring doesn't apply. This is not a trinomial, so that stuff isn't happening. So now difference of squares, well, it's not a difference of squares. This is something different, so it doesn't work. So we don't have any tools for this kind of thing. Okay. F. Ooh, mama. Fractions. Now, fractions are just numbers. And we're not stressed by numbers. We're fine. Fractions are all right. And in fact, what you should see right away, which is why we did it like this, is these are clearly squares facing, staring you in the face here. We have 49 on top of 64, 81 on top of 25. 49 is 7 squared. 64 is 8 squared. 81 is 9 squared. 25 is 5 squared. Difference. Here's a y squared. That's fine. Uh-oh. Why to the 4? Wait a minute. That's different than before. I was expecting x squared. So is this a problem? Normally I would say to myself, well, let's approach it the same way. So, is it a difference of two squares? That's the question. Well, I've already talked with fractions. 7 over 8. I'll leave that x to the fourth thing alone for a second. 9 over 5. And this one's clearly a y, right? Okay. Now, how do we deal with this x to the 4? Well, man, x isn't enough because x squared would be x squared. But wait a minute. X squared squared? When I'm do the power of a power like that, right? X squared squared, that's x to the 4th. Oh my, it works. Wow, So, in the end, we can say it is factorable, and in the front of each would be 7/8 x squared. And the back is going to be 9/5 y. Wow. I mean, is it really that much more of a wow than the other stuff? The fact that it's fractions looks ugly, but it's not exactly harder. It really just means we have a few more perfect squares than we had show up there, right? All right, looks good. How bad? Now we got down here, and I think you have just 2 more. Yeah, okay. So what do we have here? We have 20a squared b minus 500b. Now, I feel bad. I forget often to actually, well, I don't forget often. I think I say it more often than I don't. But we should always be approaching these in general like problems that should be factored, not specifically a difference of squares factoring, just because we're in the difference of squares section. But the way we're working this, we're in a course where everything we've done is still fair game. So whenever we're faced with a chance to factor something, we always want to do common factor first, then check for trinomials and difference of squares. So can I common factor this? Well, yeah, I see 20 and I see 500, right? 20 and 500, for sure I can divide by 10. So we can try that. In fact, 20 goes into 100, so 20 goes into 500 for sure, right? So I'm gonna pull out 20. Okay. Oops, I need my pen. I'll do orange this time. Equals 20. Um, a squared, the other guy doesn't have any a's, right? There are no a's over here. B and B. B and B. So I'm gonna pull out a B as well. 20b. Okay. 20b means I have a squared in the front left over, right? After I factor out the 20b, I'm left with a squared. On the second term, 500 divided by 20. That'd be 50 over 2. That'd be 25. And I factored out the b, so that can be closed up now. All right. Now we always ask ourselves, just like we say, hey, at the beginning, can I common factor? We always ask ourselves after everything's been factored, can I factor further? Can I do it again? Can I make it even better? Can I make it even more compact? Can I simplify this thing further? And yes, right? The 20b is kind of just sitting there. We're done with that. But we always, in the brackets, sometimes stuff can happen. This could have been a trinomial, right? It could have been that we only factored out 20 and now we see we could factor out the b, right? Could have done that. So what we have here is a squared minus 25. That is a difference of a squared and 5 squared, right? So this can get better. 20b is still there. But the a squared minus 25 turns into a squared puts an a in the front of each. 25 puts a 5 in the back of each. And that's that. And now I can no longer factor further. And so now I'm done. All right. 16 to the 4th minus 1. Now the front of this looks familiar. Kind of looks like this x to the 4 thing going on up here, right? Did I have that show up again before that as well? No, I did not. That was the first time. Okay. What makes this different is not the 16x to the 4th. We've dealt with that before. What makes this a little different is the back. 1, which kind of looks like nothing's going on back there. That's not exactly true. 1 is a perfect square, isn't it? 16 is 4 squared. X to the 4th we've shown is x squared squared. 1 can be written as a perfect square, though. What times itself gives me 1? 1. So while this did at first look like it might be a little bit tricky, turns out it's maybe even easier than we thought. Nice. 1 squared is 1. 1 is a perfect square. Cool. All right. So at the beginning, we saw there was nothing common. And then we said, well, it's not a trinomial, so it's a difference of 2 squares. Oh, no, I'm writing on the board. Stop. Undo. And then we proceeded to do this. And now we've arrived at, oops, hand tool. Now we've arrived at 4x squared plus 1 times 4x squared minus 1. And we can then say, oh yeah, we're done. Wait a minute. We're not done, are we? Not done. We're not done because this guy is still a perfect square. So while the other one is not, the other one is a sum of 2 squares, which is nothing. The second one is still a difference of 2 squares. So we do it again. Do it again. So I'm going to erase this underline because I don't want it out of here. Okay. Well, the first one's just going to still be there. There's nothing to do, so it just keeps coming along to the right. But the next one can be factored difference of square style again. A 1 in the back both times because 1 squared is 1 still. Square root of 4 is 2. And x squared means I got an x in the front. Nice. Okay, so 16x to the 4th minus 1. We do a difference of squares 1 round right here. And now we notice that the second one over here can be done again. And so while the first just sort of comes along for the ride, the second one splits off into these other two as well. Neat. All right. So now hopefully this helps. There's a nicer handwriting version of this note in the stream as well. But there's homework to be tried. As you might have guessed, this stuff is pretty quick to do in the homework. So, yeah, today's homework, should you attempt it, should not take as long as usual. But like we repeatedly say, I don't expect you to do everything all the time, but I do expect you to try something every time. Okay, there you go. Give that a shot, and I will see you tomorrow.